Now, I'm immediately now going to bring this section to a conclusion by covering a topic which is a mandatory experiment. Will you all heed it, please, as we go through it? It's very, very important that you'd be aware of this, that you could work on this and that you'd have something as regards what's happening. I'm talking about measuring the relative molecular mass of a volatile liquid. And we need to have some idea as to what I'm talking about here now. This is propanone. It's mentioned on the syllabus, often known as acetone, and its formula is CH3COCH3. You really don't need to know this at this stage, but let me give it to you anyway. CH3COCH3 is propanone. And this liquid is selected for this experiment because it's volatile. Now, that's a question for you. Could you define? Because they surely ask you to explain the underlying term, a volatile liquid. And a volatile liquid is simply a liquid that has a low boiling point, that is easy to vaporize. And you're a chemistry student, so you should be able to explain why something would have a low boiling point. Do you know the part of the course you'll go to justify this? It is intermolecular bonds. If the intermolecular bonds between the molecules are weak, then the molecules are free to fly around the place, and consequently what is going to happen is you are going to have them vaporizing very easily. If the molecules stick together, then you'll have to heat them to a much higher temperature to get them to gasify. And ultimately, that's what we're trying to deal with here. Now, when I've this done, I'm going to do a number of exam questions on it. It's very popular. It's on the paper somewhere nearly all the time. It could come up in question 3 on the paper, or it could come up within another question in section B. Now, it's a very popular one because there's lots of ways of asking it, and it does test your understanding of chemistry. It's quite discriminating, so I'd ask you not to take it for granted. And the minute I mention the word mandatory, your attention should go up a peg in terms of, I need to be careful. When it's mandatory, the examiner has a reasonable expectation. You're quite familiar with it. Right? So it is important that we go through this with some sense of what we're doing. To measure the relative molecular mass of a volatile liquid, propanone is the one they recommend. That's this guy, okay? But you could use other ones. You could have used ethanol, for example. That would vaporize as well. Will you be careful, please? Ethanol. The problem is, if you take a molecule that hasn't a low boiling point, if it's not very volatile or not volatile at all, then your methods of heating it will not be practical in a school laboratory. So you're going to use something that has a fairly low boiling point. The boiling point of propanone is fairly low, right? I'll just say in the 50s, okay? Mid-50s, right? Would be reasonable for that. And this one is higher. It's about 80. 70 something, right? About 80 ethanol, depending on purity now, boiling point might vary slightly. But you can imagine if you're trying to vaporize that, you'll have to heat the hell out of it because its boiling point is higher. If something has a lower boiling point, generally speaking, you'll find it will volatilize or vaporize very easily. If I take the lid off that, you'll get quite a waft, you'll get a vapor from it straight away. Volatile liquids vaporize very easily, and that would be rather important that you do that, okay? Now, here is the procedure then, and we need to understand what happens. You basically have to get the mass of a flask full of vapor. You have to fill that flask with vapor. Now, that's not as simple as it sounds. I'm going to show you the apparatus here in a moment, and we'll look at it more closely. I'll camfer the camera in a moment. You can take a look at what I'm doing, okay? But it's important that you have some sense of what's going on here, right? You basically end up, my phrase is, a flask full of vapor. You know, and that's a cliche. That's what we need to get, a flask full of vapor. Okay, and get the mass of that flask full of vapor, and you're on your way to calculating the relative molecular mass. It sounds very simple. You have to be careful of what you're saying. Now, do you understand what that means? Like we'd say a spoonful of sugar. Those of you that have been in my class already are smiling now because you know that's one of my cliches. Okay, a flask full of vapor is an important idea, but that's what you're trying to do. Nearly everybody uses this method. I'll allow for the possibility that 1 or 2 of you might have used another method. This is called the Viewmaster Method. The other method, will you take it was the steam jacket method? I'll deal with it separately. I'll show it to you in a moment, but I'd rather you'd all focus on this one because it's more mechanical. The more mechanical things are generally, the easier they are to communicate. And that will be part of your strategy when you're preparing for an exam, so be careful with that. So here's what you do then, basically. You take this flask. I think I can just take it off for the moment, and I'll go back later with it. I have the flask on a clamp here for a particular reason. You take this flask, and you prepare it for the experiment. It's a regular conical flask. I have put tin foil on it and I have elastic band around it, and I have a tiny pinhole on the surface of that. Okay, so that's what you have. That's an empty container, glass flask, elastic band, and I have the tin foil around it. Okay, so I literally weigh that on a laboratory balance. Ideally, a 4 decimal place balance will settle for 2 decimal places. You weigh the empty flask. Have you got that? That's what you do. That's the initial thing. And there you are. The mass of the flask, the tin foil, and the elastic band for this experiment came out to be 105.11. 105.11 grams. Okay, fine. That's a recorded value. They'll probably give you that on the paper. Now what you must do next is you must basically arrange to fill this flask with vapor. And what you do is you take some of your liquid, this is the one I showed you already, propanone. You take some of this, take off the top, pour some liquid into this until you cover the base of it. You don't need much in there now. Cover the base of this with some of that liquid. The exact amount doesn't matter. And put the lid back on and place it in the apparatus as shown in the diagram. You have a hot plate, right? And you have a water bath. And basically, you will mount that there like that, and you'll proceed to heat it in the boiling water. And you have to watch that liquid very carefully. Now, I'm just going to put that in there for a moment and remind you a few things. And maybe I need to lower my camera a little bit just to make sure you can see what I'm working with. All right? So let's just do that for a moment now and see, can you deal with that? Is that all right, everybody? You can see that, okay? You can see my heater. There's the electric heater, there's my water bath, and there's my flask. All right? Now, just realize what's happening here now is you have this liquid, which is boiling, and this one here is vaporizing. And of course, any excess vapor is going to go out through the pinhole in the tin foil on top. Okay, very important. So what you do here next then is you watch this very carefully, this liquid inside the flask, until such time as the last drop of it disappears. Now, that's a very important idea, the last drop disappearing, because when the last drop disappears, you have a flask full of vapor. Okay, very, very important. Now, you've seen the apparatus. I'm going to bring the camera back up again. I think you generally have the idea as to what's going on there. You proceed to immerse it in water, and that's very important, all right? Just want to bring it back up so I can use my board. All right, and there you go. So you have a flask full of vapor there, and that's rather important. Now, let me remind you, as we're going through this, that, you know, when you're looking at that now, you must be focused, and it will gradually disappear over a period of 4 or 5 minutes. It's going, it's going, it's going. It's gone, okay? And you'll make a decision. The moment that all the liquid is gone, you must take it out of the water bath. Now, can I remind you of something about this? I have a retort stand and a clamp here. I'll talk to you about the diagram in a moment now, but it's vital that you understand. If you put a little liquid into that and you put this into a beaker full of water, it will float like that. It won't. You'll have to clamp it to submerge it, because you need almost all the flask needs to be at a temperature of 100 degrees, boiling water. So it's very important. My diagram now is flawed deliberately. I'm going to come back to that in a moment. But you're watching this liquid. As the liquid gradually disappears, you're watching it very closely. And at one point along the way, it's going, it's going, it's gone. The moment it's gone, you have a flask full of vapor. What could happen there? If it wasn't all gone, then you'd have a flask full of vapor and some liquid left over. Or if you left it there too long, you would not have a flask full of vapor, because some of the vapor would have escaped through the pinhole over a period of the extra time. So it's very important, your judgment here. It's probably the single biggest source of error in the experiment, that you would take the flask out too early or too late. You take the flask out when there's no more visible liquid inside in the base of the flask. At that point, here I go again, you have a flask full of vapor. And you take it out, just take it up above the retort stand is fine, and clamp it there and leave it cool. That'll be fine. You just pick it up, clamp it, and leave it cool. That's what you do for a period of time. Okay? And what will happen when you leave it cool, when it's out of the boiling water? The vapor in there is going to condense and go back into the flask. So the vapor will be at the bottom of the flask. And, 5-10 minutes later, you take this away and you weigh it. Now, if you're going to weigh this again, let me remind you of something, please. Let me remind you, if you're going to weigh this, you must dry the outside, dry under the tin foil. There must be no water here, and it must have cooled fully. and there'll be a condensed vapor in there. Have you got that? The vapor will have condensed back to liquid. So there'll be some liquid left back in there. It was the vapor originally. That is basically the flask and a flask full of vapor there. So what do? You weigh this again now, and there is the second one there. The mass of the flask, the tin foil, the elastic band, and the condensed liquid. The condensed liquid, you could write in there if you wanted, the flask full of vapor. Okay, the flask full of vapor, and it was that. And thankfully, it's bigger. Okay, now if you weren't attentive enough to that now, you could lose some of the vapor, you could find your mass was significantly incorrect. So be careful, won't you, with that as you walk through it, right? So that's that. And so by subtraction then, in due course, you'll get the mass of the condensed liquid or vapor, and that's the difference in these two numbers. All right with that, everybody? Now, you have to, of course, you realize, of course, we have to do a calculation here. We're trying to get the relative molecular mass. We're trying to get the MR. Now, this is based on the last few classes. The MR of a volatile liquid. Okay, it's the MR of a volatile liquid, the relative molecular mass of a volatile liquid. Now, are you okay? Now we're going to call on stuff now that you need. What do you need to know then? We have a volume of liquid, okay? We need to get the volume of the vapor in the flask. We need to get the pressure of the vapor in the flask, and we need the temperature of the vapor in the flask. Now, my diagram is riddled with errors, but I am here to defend it. In the leave insert, you'd lose a lot of marks here now. Let me tell you about all the likely errors you'll make here now. You need to show clearly that the apparatus works. That flask would not sit like that inside in the boiling water. It would float, it would be buoyed up. So much of the vapor would not be at 100 degrees. It's essential that you have most of the flask under the water. Now I'm going to draw this again deliberately now to give you some ideas of what's happening, right? You draw that and your flask would be in here. Right, that's what you have. Don't forget your pinhole there, okay? Very important. Now, these are the kind of errors now. People put the water in there. That's lovely, okay? Except you've lost marks straight away because not all the vapor is at 100 degrees. It's very important. The level of the water is clearly at the top of the flask or near. It can't be submerged, obviously, because water will go through the pinhole. But it must be very high. That's one aspect of the thing now, that the detail that must be there. You label everything now, by the way. The next thing I'd say to you is, I would be putting a clamp on that. Nothing fancy now, but something like that, and tell me it's a clamp. They know you have the cop on to realise that that won't sit there in the water. It needs to be restrained, and therefore just mention that, like I have done there now as a clamp. Nothing fancy here now at all, no fancy diagrams, but make it fairly big. That should be at least a third of an A4 page now. Okay, that's the second detail, okay? I'm pointing at the details now you must have, all right? The pinhole is a detail. You must tell them that there's a pinhole there. Your drawing isn't that good, okay? So you need to basically show them the pinhole there. Now, the water level, the clamp, the pinhole with the tin foil, of course, involved, very important. And wait for it, you should, of course, show your intent. Put a thermometer inside there. Put a thermometer into the water. Okay, we all know water boils are very close to 100, but it might be 98 or it might be 99, okay, depending on the bubbling and what have you there. But just take it, will you please, that, you know, you're looking at something there and you're just showing intent by doing that, right? Now, all the common errors in this, of course, is people forget to put the heater in here. Okay, some people forget to put the water in there, by the way, that's hilarious, okay, when they put the conical flask on top of a heater. Okay, the thing will disappear instantly. You can't do that, okay? And you don't have any temperature for the vapor when you're finished. The vapor is in there, remember. At the very end, the vapor is in there, okay? And you have a flask full of vapor, and you want to get the mass of that. Are we okay, everybody, then? That's what you'll be doing. You have to clamp it so that it's submerged. They often ask this question, what is the unavoidable error that can be made in this particular experiment? The unavoidable error. And the answer is that a small portion of the vapor is not at 100 degrees because you cannot submerge the flask in water. Now that's very important that you have a sense of that, okay? That, you know, that you have it fairly high. And as I say, it's quite hilarious when you find the level of the water down there. You're talking about someone who doesn't know what they're doing. And that would be a serious mark deduction. Now all the others would lead to mark deductions as well. Anyone who has been in my class before knows anyway that, you know, you label everything. You assume the reader has no chemistry. And if you do that, you'll do very well. And I'd suggest now that that's the way you're going with that, that's your diagram. Now, it didn't take me long to draw that, except what's missing clearly from my diagrams are labels. Okay, labels. Okay, you can refrain from the bubbles if you like, guys. Okay, but it looks lovely, doesn't it? But you label everything. Everything, okay? You must understand, I'm here to defend anything that's here. So if something is missing, I can tell you. But in an exam, that wouldn't do at all now, even though anyone would look and say, I know what you mean. But I'm sorry, you won't get any marks. Okay, it must be stated or shown, and that's where labels are very valuable. That's a tin foil lid with a pinhole in it, okay? That is a retort clamp, just a clamp, call it a clamp, okay? That's a thermometer, that's boiling water, and that's your heater. Okay, and that is the vapor in there, okay? That's the volatile liquid, and you're waiting for that to disappear. Now, we're ready now to look at calculations, but remember the narrative part of this is very important as well. So look at all the details here now. I have the mass of the condensed liquid or vapor by subtraction. Now, how did you get the volume of the flask, they'll ask you. And the answer is, at the very end of the experiment, when everything is done, okay, take off the lid, chuck out the vapor, the condensed liquid that was there. Fill it with water, and please say, fill it to overflowing. Okay, fill it until it's full. We don't be like, this is a 250 flask, 250 is here, and we consider that full. If you bought a commercial product of anything in a bottle full of Coke, okay, it's not full as in overflowing. You must fill it to overflowing. Tell them that. Fill it to overflowing, pour it into a graduated cylinder, and read the volume. 3 marks, 6 marks for that kind of thing, depending on the year. Okay, very important. Next, the pressure of the vapor in there. Now, what is the purpose of the pinhole? Up to now, I've chosen to ignore that. What is the purpose of the pinhole? The purpose of the pinhole is to ensure that the pressure inside is the same as the pressure outside. Okay, let me just say what would happen if there was no pinhole there. If there was no pinhole there and you started to heat the volatile liquid in boiling water, it would vaporize, there would be a gas in there, the vapor, and it would blow the lid off the top of this flask, just like with the champagne bottle. Okay, it would go pop, and you don't want that happening. So the pinhole prevents that happening. It equalizes the pressure inside and outside. Okay, and that's very important. So, if you want to get the pressure of the vapor in there at a particular time, you basically go to the nearest barometer and you see what today's atmospheric pressure is. Indeed, smartphones allow you to measure, to read the barometer now, to read a barometer and say what the current pressure is in this room on this very day. Okay, but you use the word is barometer and you must say that. Okay, you could well suggest that you would ring the Met Office and tell them where you are, and they would give you the current atmospheric pressure from a barometer. But you'd have to mention barometer, okay? Because that's what they'll be looking for the pressure. So it's equal to atmospheric pressure on the day. I've written this down here as 750 millimeters of mercury because I'm using a mercury barometer. But I'm saying it to you now. They won't do that to you in the Leaving Cert. They'll give you the metric unit. That's 100 kilopascals. Now, don't worry about it. They'll give it to you in pascals or kilopascals for calculation purposes. And the temperature, of course, is the temperature of the boiling water. Don't be surprised if they have told you in the question that the water was at 99 degrees or 98 degrees or 98.5. Okay, by all means, if you're just describing something, suggest the water is boiling, so it's 100, that's okay. But they may give you a specific value. How would you measure it? I've told you already. You put a thermometer in here and leave it there. I have a thermometer there, a little electrical thermometer, and that could be immersed in the water and left there, okay, next to the flask while it's going on. Now, none of us do that, but don't tell anybody. Okay, we don't do it, but I mean, you have to show intent, and that's very important, right? You have to show intent. That's how you measure the temperature. Now, there's easy marks for this, guys. I'd like to think you'd all work with it, with the attitude that you could score very well in this question, okay? Now, what about the calculations on it then? We have to look at them just in how you might go about them. I'm going to put a set of calculations here on the screen for you. There are two ways of doing it. You probably know at this stage, listening to me, that I have a preference for the ideal gas equation. And I hope that you might work with that. Now, I hope you can read this. This is all I'm going to show you is this piece here. And I hope it might be okay. I'm hoping you can read it, okay? Now, maybe I need to do something like this with you now. The volume of the gas. Now, don't worry about the details here. All I want is the calculation with you. Maybe I'll just show you that piece. Okay? That's all that you need. Let me raise that a bit for you. There, like that. PV equals nRT. I'll write it here again to make sure everybody's okay. PV equals nRT. And you're going to have the pressure of the vapor from your barometer. You're going to have the volume from the capacity of the flask. You're going to have the temperature from your thermometer, and everybody knows R, so you're able to go and solve for N. Now, I've this done previously, so I needn't hang around here. N equals PV over RT. Okay, and you proceed to put the values in there then. Okay, be careful now, please. This fellow must be, are you ready for it? This fellow must be in meters cubed. So if the flask happened to have a volume of, it doesn't matter, supposing it had a 295 centimeters cubed. Remember, the flask is 250. It's 250 to here, so you'll have all that piece as well for the vapor. So 295 or whatever, right? It'll be given to you likely in the exam. That's equal to 295 by 10 to the power of minus 6 meters cubed. Now, I'm saying it again to you. I know that's not correct scientific notation, but the calculator will look after that. That's the conversion factor. You must go to meters cubed. Okay, the pressure is in likely to be in kilopascals, and you must go to pascals. Will you be careful, please? PAs. It must be in pascals. And the temperature, of course, will be in degrees Celsius. We'll say it was 99 degrees Celsius given on the paper. Then, of course, that will be adding 273 to that. So you're going to get 372 Kelvin. So you'll have Kelvin, pascals, and meters cubed. And you pop them into your formula, and you're going to end up getting a value for N. Okay, and N will come out to be a certain value in that. Let me just show you that because I think you need it. All right, N. You solve for N there, and N comes out to be a certain value. I'll take the one here that's on the screen. It doesn't really matter. I have 0.0016. I'll leave it at that. 16 moles. Okay, when you solve for N now in this formula. The pressure in pascals, the volume in meters cubed, the temperature in Kelvin, and R is always metric 8.3. Go and solve for N, and it comes out to be that. Now, as it happens, you know the mass of that many moles. You know the mass of that many moles, and this is all done. We did a calculation in the last unit, and it is basically preparing you for this. Do you know what you're going to do now? So you have obviously two masses already, which you work from, and they're very important. I'm going to put them back again for you now because I need you to see this. Okay, I'm putting back I have another method of calculation here which I'd rather you didn't do. I'll talk to you about it in a moment, but it's very important that you can deal with that now. Sorry, now just bear with me a sec, please. We have the mass here, okay? That was the first mass of the empty flask. This is the mass of the flask with it full of vapor, a flask full of vapor, okay? And by subtraction, you're going to get the mass of the vapor. So that many moles, 0.0016 moles has a mass of, calculated there, of 0.61 grams. So 1 mole has a mass of X grams. And you solve for X, that's cross multiply. Most of us will do that, will you? You'll multiply that by that and that by that and solve for X. And X is the relative molecular mass. Are we okay? That would be the relative molecular mass. What is the relative molecular mass? It's the mass of 1 mole. Okay, now it's very important that you are aware of this because they can play with your head on this. I'm going to look at some exam questions on it, and I think it would be very important as we go through it that you'd have some structure in place for that. Now, I think we're doing okay, but I think I need to treat the experiment first of all as procedure, and then I'll do a unit on calculations on it because I think you need to be sharp on this. Now, I would say to you that this has come up nearly every other year on the exam paper. Last year, 2019, it came up in question 3, a full question. It's very popular because they have many variations of it, and I will need to look at 1 or 2 variations in due course for you. Okay, so that's fine. Before I finish with this particular category, will you look at this calculation here on the screen for a moment? I'd rather you didn't use it. Now, sorry, you may have difficulty seeing it, but if you use the general gas equation, okay, if you use this one here, the general gas equation, P1 V1 over T1 equals P2 V2 over T2, you could indeed work on the basis that you have a pressure, a volume, and a temperature, and you could calculate the volume at standard temperature and pressure. Okay, and from that you could calculate the mole. Now, I don't want to hang around with it, but basically there's the volume. So that volume had a mass of that. So 1 mole is 22.4 litres at STP, has what mass? Now, if you want my opinion, that's a bit more tedious. The one thing you have to watch for in my method, the method I've asked you to use here, I'd prefer you use that than this. Now, I've no problem with that. The units don't matter here at all as long as they're the same on both sides. But I would suggest to you that's more direct to your destination. The one problem with that, please everybody, always have an alert mark there on that, metric. Everything has to be metric in that because R is metric. You have no question, your units have to be right here. Now I spoke to you in a previous unit about that, I won't hang around, but please make sure you wouldn't make that mistake, okay? And you should still be able to get the MR. By the way, the MR here comes out to be 58, and I wonder, are you okay with that? Now there's an alternative method of doing it. I better just mention it briefly in case any of you have used this method at any stage before. I'll just show it to you briefly. Now before I start, can I say this to you? You don't need two methods. And you can do it by any method, provided you describe it correctly. The second method involves basically a gas syringe in a steam jacket. And I'll just show you briefly what that is now. This is the gas syringe. I had one in class the other day for you. Do you see that? But it's wrapped around, I'm holding it on the outside, by a steam jacket. And what's that? It's a glorified container around it. You put the steam in one end and it goes out the other end. Now suppose you connected that to a steam generator. That would be a glorified boiling kettle with this connected to the spout. And the steam would go in here, it would fill the outer chamber, and the steam would come back out here through this one, okay? It would come out through this one. And that's what you'd have. So you'd have anything in there then would be at, could be at the appropriate, could be inside in the steam jacket, so it would be at 100 degrees. Now, I need to tell you something about this then. This probably isn't used much other than as a demonstration, so I have to be careful with you. So what you would do is this, you'd put some air into it at the beginning. Now, please, if you're taking the other method, don't worry about this, just give me a moment so I can show you. I'm leaving that at 40, okay? There's 40 centimeters cubed of air in that. And now what you do then is, you get the volatile liquid and you put it into this. That's a hypodermic needle. Okay, now please let me put this down a moment and show you what you actually do. The thought is probably striking you now is that I know why we don't use this in class. This will be very dangerous in class now. You need to be careful because obviously you have a needle here and we're going. You'd basically suction in, you get rid of the air first. You'd suction in some of the propanone, the volatile liquid in here. Are you okay with that? That's exactly what you do. Okay, and you put a safety cap back on it again. And you'd weigh this. You'd weigh that. And what would you do next? You would now inject a small amount of this into the gas syringe, which is in steam, which is in the steam jacket. You'd actually push it in through that there like that, and look, you'd push in the piston, and you'd see the other piston going out. Okay, and what would you do then? You basically would find it expanded from, it would have gone from, we will say, it was at 40, and it might go up to 65. So you'd have 25 centimeters cubed of your volatile liquid in there. And how would you get the mass of the vapor? Easy. Having injected this into the gas cylinder there, into the gas syringe, you would weigh this again. You weighed it at the beginning with some volatile liquid in it. You injected some of it into that, and it expanded, of course, with the heat. And then you weigh this again by subtraction of the mass of that. Now, I'm going to say no more to you on that, other than you can see, sorry, from here. Let me just show you. You can see from here what we're actually dealing with. That you'd inject it in there, that would move from here to here, and that would be its volume. Its temperature would be the temperature of the steam. You could put a thermometer in through a side arm here for that if you wanted. And, you know, the pressure would be the pressure of the air because the piston comes out and it stops coming out when the pressure of the air is equal to the pressure of the gas. Now, I'm not for 1 minute saying one method is better than the other. That last one I showed you is probably a bit more accurate. It won't gain you any extra marks in the exam, and it is far easier, I think, to describe the more mechanical one. I'd strongly recommend that the flask full of vapour would be the more reliable one to use in Leaving Cert for the marking scheme. Okay, but the other one is there, and some of you in different schools might have used that on occasions, so be aware of that, okay? And we did nothing to add to it other than that. Now, there's the way the calculations would work for that then, just to give you a look before I finish. The temperature of the vapour, 100 degrees, had to convert to Kelvin. The pressure was atmospheric pressure, and today it happened to be that, which happens to be converted. Now, they give you metric in the exam for pressure. You won't be working with millimeters of mercury. The volume of the air in the syringe before you inject it. Okay, there was a certain amount of air in it, okay, I had 40, okay, there's 10 here. And the volume afterwards, when you injected the volatile liquid in there, it vaporized and pushed the piston out. The final volume was 60. These are makey-uppy figures now, they're not very accurate because I've rounded them off, okay? So the difference in the two of them is the volume of the vapor. Okay, that would have been the volume of the flask in the other one. There you go, it had to go to meters cubed. There's your formula, and you're going to solve for n in that. The initial mass of the syringe, okay, plus the liquid, the final mass of the syringe and the remaining liquid, and the difference is the mass of the volatile liquid that was vaporized. And so the calculation then goes from there. N equals PV over RT. And you put in your figures all metric, and look, n came out to be 0.001634. Now, I've told you in a previous unit that the mole is huge, so don't be surprised if you're getting values like that for moles. 0.01 isn't unusual. That will still be a good bit. I told you mole is huge, and consequently you can expect a small amount of moles here. So that many moles has a mass of this. So 1 mole would have a mass of what? And there you are, it came out at 61. 61. Now, I wonder how good that would be as an answer, 61. I've told you the formula already, and have you all done a quick calculation on that? If you did, you'd find out very quickly. 1, 2, 3. 3 carbons is 3 by 12. 6 hydrogens, 6 by 1. And 1 oxygen is 16, okay? 36. 6 and 16. That's 58, I think, and that's not bad at all, okay? That's not bad at all, 61. Experimental error, it's called. Well, that's my line anyway, okay? Now, that's very important, and I think, you need to revise procedure and practice there now before you start delving into exam questions on that.